Welcome to our last lecture in the course on finite element methods. The topic today is how wrong is right enough. So we want to talk about error estimation and what you can say about how good the approximation quality of your FEM even is. Also, this is going to be the end for the course. So the outline for today is we're going to start with asking what's wrong with our FEM, so observing when things go well and when they don't. Then we want to consider some theoretical results, in particular Sear's lemma and some optimal error bounds on how to estimate errors. Then we want to do a practical convergence study, and then in the end, of course, because it's the last lecture of the semester, I want to give some final remarks for the course as to summarize everything and wrap it all up nicely. So let's start asking the question, what is wrong with our FEM? Because so far everything looked quite well. And now I want to show you what is going on if we get errors and what the limitations are. So let's see. Firstly, I want to show you two similar examples, but they are not so similar in terms of the behavior. As for the setting, I'm switching to a simple one-dimensional setup where the domain is just the interval from 0 to 1. The reason for this is that in one-dimensional settings, it's relatively simple to write down exact solutions for certain problems, which is not the case in higher dimensions. So let's see, we have two examples here, and the procedure, the way I constructed the examples is such that we know the exact solutions. Okay, the first thing you see here on the left-hand side, the example number 1, just with a constant f as 1. This is something you've seen before. This is the typical parabola shape that you have seen in different simulations before, so it's easy to construct the solution from simply integrating and then inserting the boundary conditions. And here on the right-hand side, I started with the exact solution and I computed the right-hand side f such that it fits into the boundary, into the partial differential equation. That's also very common. When you want to talk about errors, it's usually necessary to know the exact solution. That's why in practical examples, you often start with exact solutions and then derive the PDE from it. And then what I've done is I've used a standard piecewise linear finite element setting and computed the FEM solution on the interval from 0 to 1 with just 10 steps. And what you see on the left side here is the parabola shape of the exact solution is represented. You see, okay, there is some gap here in between, so the maximal value for our numerical solution is roughly 0.1, while the exact solution has value 1/8 in the middle here. But still, the solution shape is represented, and kind of the error is small in a sense. However, on the right-hand side here, we observe something quite weird. So this blue line here, the exact solution, is the sine curve with the high amplitude, with the high frequency here. What you also see is that the amplitude is just the regular 1 and -1. So it's almost a flat line here because the maximal and minimal values of our numerical solution are above 75. And what it also shows is not only a problem in terms of the absolute values of the solution, but also it does not at all represent the frequency of our sine curve, because the numerical solution looks as if we would consider just sine of 2 pi x, so just a single sinus, just a single sinus interval. But the actual real solution has many of them. So here's a lot that's going wrong. And if we measure the error in an L2 norm, So in the sense that you take the difference between your exact solution and your numerical solution, and then you integrate this over the whole domain. So you just take the integral over u minus u star, take this square, take the square root out of this and integrate this from 0 to 1. That's our L2 error. Then here on the left hand side you see this is 0.05. It's in a sense close, and you would say, okay, well, for 10 points this is pretty decent. On the right side here, the error that we can already observe by looking at it is also given here, because we have these huge values and the error is enormous. So 176 as a value for the error, that's in a sense more than you would have for the actual integral of the analytical solution. So here we have a huge error. And the question is, usually we don't know the exact solution. So how can we know anything about the error? How can we quantify anything that tells us how good our approximation is if we don't know the exact solution? That's the topic for today. And right at the beginning, I can tell you this is not a simple answer. So we have a problem. If you're hoping for any exact error quantifications, in the sense that if I do some finite element approximation, then my error is going to be 0.5 or 0.05 or something. That's not going to happen. As long as you don't know the exact solution, there is nothing you can do in terms of exactly quantifying your error. But I wouldn't be giving this lecture if there wasn't anything we could do. What we can do is we can try to find upper bounds and estimates. So in a sense, instead of actually quantifying the error, we want to try to bound the error from above, which is also fine, because if you know that your error is smaller than something, then it's usually fine, because if the error is even smaller than that, it's not a problem. So we want to today try to derive certain error bounds, and still the results may not be that satisfying, because what I can already tell you is you're not going to have a result that looks just like error is smaller or equal some constant. So these 3 points here are what are the topic of today's lecture. So we want to find out what is necessary as for a qualitative description of the error. So let's start by looking at some theoretical results as a groundwork to analyzing our errors. And the first important result is Sear's lemma. That's usually the part where you start when you talk about errors in finite element approximations. The first thing that you can look at is this lemma. And let's look at it quite slowly. Okay, the setting is we are in a Hilbert space, and we have a bilinear form and a linear form. So the setting that you have all seen in the lemma of Lax-Milgram, you have a Hilbert space V, you have this calligraphic B as a bilinear form, and you have an L, which is a linear form. Then you also claim that B is bounded and coercive, and L is bounded. And we're going to look into the details in a minute. And then we denote the unique solution of the continuous problem of finding U in V such that B of U in V equals L of V for all V's. That's going to be denoted by U star. That's going to be our exact or the solution of the continuous problem. On the other hand, the other problem that's more at hand for us is the discrete problem, where you do the exact same thing of finding something, but only on a subspace VH. So here VH is a subspace, and usually, that's why it's indexed with H, usually it will be chosen to be finite dimensional for example, the space of piecewise linear functions on your domain. And then the result is that this inequality holds. Okay, what can you see here? The error that's printed on the left-hand side, so the norm of the difference between the exact and the numerical solution. The error is bounded from above by some constant and then times the infimum over all functions in your discrete space of the error with respect to this other function. What does this mean? Well, it means that if you compute your solution for the discrete problem, the UH, that's almost the best you can do in your respective space VH. And that's pretty good, because so far we didn't quantify at all if our finite element solution has anything to do with the exact solution. It could have just been some random piecewise linear function that was completely unrelated to the exact solution of the problem. But this result here tells us no, it's not just completely random, it is actually almost, except for some constant, the best you can do in your given space. And that's pretty good. So let's look at the details here again. So what's the setting? Usually we talk about V equal to H10, so our space of one's weakly differentiable functions with zero boundaries. But of course, if you have a certain problem where the Neumann problem is also does have a unique solution, then you can also choose H1. Then we have already in the last lecture seen that if we choose the forms appropriately, then this variational formulation of the continuous and the discrete problem, that's essentially just the weak form of our PDE. As I already said, the discrete space VH usually will be our piecewise polynomial space, and this makes UH our finite element solution, because that's exactly what FEM is doing. It computes some function in this piecewise polynomial space such that the equality or the equation holds for all test functions in the discrete space. And then those properties for B and L, B is supposed to be bounded and coercive, and L is also supposed to be bounded. Those are the same properties that we required for Lex Milgram. And that comes in pretty handy, because you think about it, you get those properties to be true, and then you have a unique solution, and Sayer's lemma is also true. So that's kind of a good deal. Okay, and then why is it helpful? That's what I already explained. It proves that we are not just giving any piecewise polynomial function as the result of our FEM, but in fact it's the almost best approximation that you can get in your given discrete space. And it's almost the best because it's only off by some constant factor. And if you look at, or if you remember our initial example number 1, where you had this this square polynomial here, and then the FEM solution was something like this. So it connected dots that preserved the exact same shape, but they were kind of off. That that visualizes pretty clearly what we're doing here. So of course you could say there is a piecewise linear polynomial that approximates our exact solution better, but our FEM solution is still pretty good. It's not in the opposite direction. It's not just the constant zero, but it's actually just off by some factor. And that's pretty good. So we can always be sure that our FEM solutions are at least in some sense good. Of course, we don't know for now how big this constant can be. That's kind of problematic. And also, in the other example with the sinus function, we are still not in luck, because if you think about this sine function, which was from 0 to 1 and had 10 whole oscillations, so something like this, then if you think about a finite element discretization with piecewise linear functions and just 10 steps in between, then, well, this best approximation is still going to be pretty bad. So you can't help anything if the finite element space is chosen poorly, because then your best approximation in the space is already terrible. So those are the two drawbacks of this result. You don't know much about this constant for now, and you also can't help it if your finite element space is not chosen well. Now, what we're going to do is we're going to prove this lemma, because I'm personally thinking that this proof is firstly rather simple and also pretty instructive, because it uses different techniques that are also kind of common when talking about weak solutions and these Hilbert spaces. So let's see, what do we have? Firstly, I want to just collect stuff. The first property we know is that U star is the exact solution, so the solution of the continuous problem, meaning that if we apply our bilinear form with U star and any V, then this is going to be the same as L of V, and that's true for all V in the whole space V. Okay, and then we have this solution for the discrete problem, and we call it UH. And there a similar thing is true, and then if we apply B of UH and VH, that's going to be the same as L of VH, and that's true for all VH in our discrete subspace. Okay, I want to mention here and I want to underline that this is only true if our discrete subspace or subspace VH that we're considering is a subspace of the original one. So if you, and that's important here, if you have a so-called non-conforming discretization, in the sense that, for example, in 2D you talk about H10 functions which are continuous, and if you consider a discontinuous discretization, then this lemma is not true anymore. So this fact that we are in a conforming situation, that's very important. Okay, so those two things are known. And what's also important to note is that if I would test with any VH in my subspace VH, then of course this U star would fulfill the same thing as well, because V is the biggest space. Okay, and now the first thing we need is we're going to talk about the so-called Galerkin Orthogonality. It's called like this because technically finite element methods constructed upon some discrete weak formulation, they are all a subclass of the so-called Galerkin methods, and that's why this Galerkin orthogonality is a property named after the mathematician that invented those original Galerkin methods. And to prove this, it's actually quite simple, because, well, also right now you don't know what the property is even, but you're going to see it in a bit because the proof is only 2 lines. So let's look at some discrete test function. Okay, so we are going to take a test function VH in our space VH. And then, that's what I just mentioned. Then we have A, the fact that B of UH, our discrete solution, and VH is L of VH. And then furthermore, we also know that the same thing is also true for our U star, because VH is a subset of the bigger space V, and this is true for all V. Okay, so we can do that same thing also for VH, for U star. And then you see that on the right hand side here we have printed the exact same thing. That's why we are going to combine those two and form the difference. So B minus A. That gives you, on the left-hand side, b of u star and vh minus b of uh and vh. And on the right-hand side, you just have L of VH minus L of VH. And then this here on the right-hand side is obviously just 0. And on the left-hand side, I can use the fact that B is a bilinear form, which means that it is linear in both arguments. And because the second argument is the same for both of them, I can simply just take the minus into the first argument. So B of u star minus UH tested with VH is just 0. That's why it's called orthogonality, because in typical scalar products, and that's what we mentioned, so the scalar product is a special bilinear form. And if some scalar product is 0, especially if you think about the standard scalar product in R2, for example, then if the scalar product of two vectors is 0, it means that they are orthogonal. That's why if we have this property that some special bilinear form is 0, then we also call this orthogonality. And what does this result particularly mean? It means we always are kind of testing with these VH functions. And of course, this is true for all VH because it was chosen arbitrarily. It means that testing only on the discrete subspace where we have chosen VH from, we cannot even measure the error. And that kind of makes sense because UH was chosen to fulfill our problem as best as possible, or as good as possible, on our discrete subspace. That also means that on the same subspace, there is no error we can measure. So, in terms of degrees of freedom that could measure the error, we don't have any, because we have used all the degrees of freedom to find a solution that is as good as it gets in the particular space. So the error when testing with only VH functions is 0. If I was using V, so some function from the continuous problem, then of course this would not be true. Okay, so the VH here is very important. That's true for all VH in the discrete space. Okay, that's a key. And now we are going to use this to prove our lemma. And what we additionally need is the prerequisites that B is bounded and coercive. And I want to just for a second write down what this means again. So B is coercive. Coercivity was the bound from below if I'm plugging in the same argument into both components. So B of V and V is bigger or equal some factor alpha times the norm of V squared. And that's true for all V in our original space. Okay, and then also B is bounded. That means B of U and V, so different arguments here now, is less or equal, so the bound from above, less or equal some constant times the norm of U times the norm of V. And that's true for all U and V in the space V. Okay, and now we can start by simply computing our result. And for this, I'm again taking some arbitrary function VH out of my space. And I'm starting with the coercivity, I'm starting on the left-hand side with something that doesn't even involve VH. So I'm just writing down the coercivity condition, and as my function V here, I'm using the error. Okay, so I'm writing down the coercivity stuff, but in my norm I'm putting the error. Okay, there is nothing that would ever stop me from this, because u minus UH is definitely something in our space V here. It's not in VH, but it's in V. So the coercivity is true, and I can simply write down that this is less or equal B of u minus UH and u minus UH again. Okay, so that's coercivity. And then we are doing a typical trick for mathematicians. I'm adding a 0. And what I'm doing here is I'm keeping the first argument constant, so u minus UH. But in the second argument, I'm inserting this arbitrary VH that I've introduced here with plus and minus. So I'm taking minus VH plus VH. And that's combined again a 0, so it's no harm done, minus the UH that I had before. Now I'm using the bilinearity, which means that I can simply take this plus out of my B. So I'm getting B of u minus UH tested with the first part here, u minus VH, plus B of, and then the same first argument, u minus UH, tested with the second part here, VH minus UH. Okay, and now it becomes interesting, because here we observe that we have a test function that is VH minus UH. And, well, it's if I have a subspace of some vector space, some arbitrary space, Hilbert space V, then, well, it has to be that for two elements of my space being in there, the difference should also be an element of the space. So if they are in VH, then VH minus UH is also an element of VH. Okay, that was a long speech, but why is that important? Well, if you remember our Galerkin Orthogonality, then we've seen that the difference between the exact solution, that is supposed to be u star, I'm going to change this for a second. So the error tested on our discrete space is simply 0. Okay, so here I should also take u star. So that's always the exact solution. But yeah, so this here from Galerkin orthogonality is simply 0. So I can write down that this is equal to B of u star minus UH tested with u star minus VH. Okay, and now I can also use the boundedness. The boundedness was usable for two different arguments. Also, I'm keeping the direction of my estimate because this was less or equal, and I'm now again writing less or equal. C times, and then the first argument, u star minus UH, times the second argument, u star minus VH. Okay, and now I'm going to put this away here for a second, and I need just some more space. So what I have now, if I combine those two parts, is alpha times u star minus UH squared less or equal C times u star minus UH times u star minus VH. Okay, and then I see here on the left hand side is u star minus UH square, and here is u star minus UH, so I can divide by this. Okay, first thing is, am I allowed to divide by this? Because if it gets 0, I am not allowed to do this. If my error between the exact solution and the discrete solution is 0, then I'm also done. Because if my error was already 0, then I'm definitely doing the best approximation I can because it's actually the right one. So I can assume that this error is non-zero. So I'm good, and I'm dividing by this, and this means that I'm left with alpha times u star minus uh without the square now, less or equal c times u star minus vh. Then I can take the alpha on onto the right hand side, and I have my result u star minus uh less or equal c divided by alpha times u star minus vh. And because this is true for all vh, because it was chosen arbitrarily, I can simply take the infimum, because if an inequality is true for all, then it's also true for the infimum. And that means that I can write down my statement now. That also means that I now know what this constant is in Sear's lemma. That's not a common case that in numerical estimations you actually know the constant, but here now it's a combination of the boundedness constant and the coercivity constant. Okay, so this less or equals c over alpha times the infimum over all vh in vh, and then this thing here. Okay. And that concludes the proof of Sear's lemma. I wanted to show you this because it is actually pretty instructive in the sense that we have derived in a straightforward way this Galerkin orthogonality, which is kind of cool and also instructive in a way. And then we have used those properties of coercivity and boundedness to simply combine everything such that we get our result in the end. Okay, so what we now know is, we have even proven it, Sear's lemma is true, so the finite element solution that we're computing is almost the best we can do in our given discrete space. That's pretty good, but on the negative side, that's what I mentioned before, we don't know what the best approximation in our given space is. So for an actual error estimation, if we don't know the exact solution, this does not really help. So it helps us in finding out that we're not just doing completely random stuff, but for the actual error estimation, for example, if you think about this example with the sinus of 20 pi x with a high frequency, there it doesn't really help. Okay, let's see what more we can do. And the next step is to look at optimal error bounds. And this, what I've written down here is a combination of different theorems and lemmata. That's why I've just combined it into a single result. And yeah, let's look at the setting. We are considering H10. And again, if you are in a case where the Neumann problem on H1 has a unique solution and you find a conforming discretization for that, this is also fine. But I've just, for the sake of simplicity, chosen H10 because then we are always golden in terms of unique solutions. So we have H10 and VH as the space of piecewise linear functions. So our finite element setting. And then we as usually denote U star as the solution of the continuous problem and UH the solution of the discrete problem. Then we can estimate the errors. So we are estimating the errors in two different norms here. Firstly in the L2 norm and secondly in the H1 norm. Okay, let's give a quick reminder. What was the L2 norm? The L2 norm of something is simply the integral over that something squared and then the square root out of it. Okay? And that H1 norm is a bit more. That H1 norm is that something squared plus the integral over the gradient of this something also squared and then the square root out of this. Okay, and what is the error bound? It involves two important ingredients. It involves the step size of your grid. So H is always the step size. And in the most simple case of your equidistant grids that we've been talking about, this H is just the division step. For adaptive grids, it's not that simple, but we are not going to talk about this here at the moment. So you have this H, and you have the H1 semi-norm of U star. And let's look into this for a second, but what's important here to note is that we have two different norms. The L2 norm only considers function values, H1 norm also considers the derivatives, and for just the function values we get H square here as a factor, and for also derivatives we only get H. And if you think about H to be something that's small, because that's usually what you're doing when talking about FEM, you want to get a small grid width, that's why H square is even smaller than H. So you kind of get a better approximation in this simpler error of L2 compared to the H1 error, which kind of contains the L2 error plus something else. Okay, let's take a deeper look into this. What's this semi-norm that we are using on the right hand side? This semi-norm is only the gradient part. Okay, if you think about the H1 norm that I've just written down again, this was a part where the function values were taken into account and a part where the gradients were taken into account. But now here this semi-norm is just the gradient part. The reason why this is semi-norm and not a norm is that it is not positive definite, because you can easily construct a function that has zero norm or zero semi-norm, but is not just the constant zero function. Because if you think about a constant, any constant bigger than zero, then the gradient of this will definitely be zero. So the integral of the gradient will be zero. So this semi-norm will be zero, but the constant one function is not zero. Okay, so we are bounding these errors from above by something that contains the grid size and the H1 semi-norm of the exact solution. So in the sense, the gradients of the exact solution. And of course, this would also be true if we would take the real H1 norm, but then this statement is less strong, because the way that we have defined this now is that our error only depends on the gradients. Okay, what this statement tells you is that the only thing that matters is how strong is your exact solution rising. Okay? So the only problem that your numerical solution, your piecewise linear functions, for example, have is if your U is increasing too fast. Then these linear functions just can't follow this huge increase. If the function values are big, this is no problem. Big function values don't give you a big error bound here. Okay? So you can have constant functions that are super big, it still gives you a very small error bound. And that's pretty instructive, because it doesn't really matter what the values of your exact solution are. The only thing that matters is the gradients. And that's instructive, because if you think about a function that is doing something like this, so a very steep pole here, then it's intuitively clear that a linear function can't follow this huge steep ascent and will give you an error. Okay, what does that give us now? Just for a second, the idea of the proof. So I'm not going to do the full proof because that's a really, really long one. Just for the ideas, I'm going to name a few important parts. The two lemmata, one of the two mathematicians Denis and Lyon, and the other one from Bramble and Hilbert. Those two lemmata combined give you the result that this minimum error of some local polynomial can be bounded from above by the H1 semi-norm. That's true for all functions. So in a sense locally, because here I'm choosing P1 of 2, so an actual linear polynomial.
and also the L2 norm only on some triangular cell T. So locally, you can get as good as you want using polynomials. That means if you have a certain cell, I'm going to draw a one-dimensional example again. So this is my cell T, the interval from here to there. And I can approximate any function as good as I want, as long as it's not increasing too much. Because then if it's increasing too much, there is no polynomial which I can find that approximates this well enough. But yeah, this statement tells you it's possible to locally approximate any function by a polynomial as good as you want. And the only bound is the integrals over the gradients. And the second part is interpolation errors. So every finite element method, which is essentially supposed to do some solution process in your discrete space, can also be interpreted as an interpolation of the exact solution into your local polynomial space. So you could always say, instead of doing some solution process, I'm doing an interpolation. It's just as hard, so I'm not making anything easier here. But for the sake of proving something, it's sometimes important and necessary to consider this interpolation approach. And then here you see that the error between some arbitrary function and the interpolate of the function, that is bounded from above also by something that contains the grid width here. And if you combine those two parts, then you can already see this always involves something with the gradients here, so this H1 semi-norm, and here in the interpolation error it also involves the grid width. And by considering this only locally, because this is L2 on T and this is also L2 on T, by considering this only locally on some triangular cell where you have this edge length HT here, that's why we have this dependence on the step size here. That's where this comes from, because we're considering the approximation properties only locally, because that's what the whole FEM is doing. It's constructing those global piecewise functions by actually looking at local polynomial functions. Okay, so far so good. Now what's positive is we can now quantify the error depending only on the grid. That's good, because we have definitely control over the grid and the derivatives of the exact solution. What's problematic is we usually don't know anything about the derivatives of the exact solution. Sometimes we do. Sometimes it's possible to estimate the derivatives. So in a sense, this is better than this SEA lemma bound with just the optimal discretization error, but it's still problematic. But usually this is as good as it gets. So we usually don't get better results, and what we have completely ignored so far is that this also tells us something about the behavior for changing grid sizes. So if you look at this result here again for a second, this one, then you see here that because H occurs here, this means that if I'm replacing H by H over 2, so I'm just taking twice as many points in each direction, then this should mean that my error, because, well, the exact solution doesn't change when I'm doing something about my grid. This constant C also doesn't depend on the grid. That means if I take half the step size, my error, U star minus UH in L2, that should be cut by a factor of 4 actually. Because H square, so you see that there comes a factor of 4. And that's a very important property, because this tells us how our method behaves if I'm using finer grid structures. So that's pretty cool, because that is called convergence. That means that our error is converging towards 0 if the grid is used in a finer way. and that's as good as it gets. Now let's look what this convergence concept means in practical. The idea is we want to verify our theoretically known error bounds, and we have those two different error bounds here, and they mean that if I replace my step size h by half the step size by simply using twice as many points in each dimension, I should see the error in h1 to be cut in half and the L2 error cut in a quarter. Okay? And also just a quick side remark, it's not a coincidence that the h1 error is decaying less strong. That's always the case. So the more derivatives you want to take into account when talking about an error, the weaker your statements are getting. So that also kind of makes sense because you can't really know what this error is doing anymore if you talk about higher derivatives. So that's why we're also going to focus on the L2 error in our studies for now. So we are trying to verify this part here. So we want to see if the L2 error is actually cut into a quarter. And what's the approach to verify this? The first thing is you need to choose a suitable test problem. The term suitable means firstly that the exact solution is known, because if you don't know the exact solution then you can't really compute any actual errors, because here now we need actual errors. And also the test problem should be bad enough in a sense. Why I've written this down is because in my studies, when I started talking about errors, I had this problem quite many times that I simply could not verify those convergence orders. And the reason for this is if you have a problem where the numerical solution converges very fast because the problem is simple, for example, the problem itself is a polynomial, and you want to approximate it by piecewise polynomials, then you are very likely to get an error that is close to machine precision. For example, in Python, this is around 10 to the power of minus 15, I think. So your error is going to decay so fast that you cannot even compute it anymore. And because as soon as you have reached machine precision, there is no way of cutting your error even further. And then what you do is, if you have chosen this suitable test problem, is you define a sequence of grid sizes following some exponential law. Because you always want to talk about h square or h to the power of 3 convergence. So you need to have some exponential law. For example, powers of 2, so 1/2, 1/4, 1/8, and so on. That's the easiest choice. You apply your FEM or any other numerical method for each grid size and compute the error. And then you plot the error on a logarithmic scale and compare with asymptotics. Why am I using a logarithmic scaling? Well, the reason is if you have an error decay that is, for example, quadratic or cubic even, then it's difficult to verify it if it has the correct decay rate if you have a linear scaling, because then you will see a parabola or a cubic function. And when you want to compare with asymptotics, so what is an asymptotic here? This means that I'm simply prescribing a function that is exactly following the requested law. So if I talk about these grid sizes, then my h asymptotic would exactly be the same numbers. The h square asymptotic would be 1/4, 1/16, and so on. And the h to the power of 3 asymptotic would be 1/8 and 1/, now I have to do some math, 64, I think, and so on. Okay, so that's what I'm comparing with. And I want to try to find out what are the, which convergence rate my method actually has. And because it's difficult to compare the shapes of parabolas and relatively easy to compare the shapes of linear functions because you can see if they are parallel or not, that's why I'm choosing a logarithmic scaling, so that in the end my error plots are going to be straight lines. And that's exactly what I'm doing here now with the test problem. And this test problem is the example 2 from the introduction. So I'm using Poisson's equation in the one-dimensional domain from 0 to 1. For my right-hand side, I'm choosing this weird f that I've constructed from this exact solution sine of 20 pi x. And that's precisely one of those functions that are bad enough. Because if you look at this simple discretization with 10 points, the error is huge. And that's really good in this case, because with this huge error, there is room for the error to decay. If the error was already small, if you think about example number 1, where you already had a 0.05 error for this very rough discretization, there it's pretty difficult to still compute the error after a couple of refinements, because then it will reach machine precision simple enough. So here we already know that this is bad. So in our case now, that's a good thing. And then we do exactly what I've just said. So I'm choosing the sequence of grid sizes from 1/2 up to 1/128. So this is following a simple exponential law. And I'm computing my error for each one of those grid sizes, and then I'm plotting this on the logarithmic scaling, and that's what you get here. So the red line is the L2 error for my grid sizes that you see printed down here on the x-axis, and on the y-axis I'm using this logarithmic scaling that I've mentioned, and those colored lines, they are asymptotics. So the blue line is following an h-asymptotic, relatively flat behavior, then the yellow line is an h-square asymptotic going a bit steeper, and then the h3 asymptotic is a very fast error decay that's going down even further. And then the question is now, what asymptotic is the one matching my red line? Well, if you look at the blue one, then you can directly see that they are crossing at some point, so that cannot be the same thing. If they are crossing, they cannot be parallel. For the green line, on the other hand, the h3 asymptotic, you see here, this distance is much smaller than this distance here at the end. So you can see that green is decaying faster than our L2 error. However, this error here between the distance between the red line and the yellow line, that's roughly staying the same. And that perfectly matches our theoretical predictions, because we can indeed observe that our L2 error decays in a quadratic way. That's what theory was prescribing. So we had this statement that u star minus uh is less or equal c times h square times the L2 semi-norm of u star, the h1 semi-norm. So of course this is also a constant in the sense here, because we have one single exact solution, so that's not changing, and we can observe that we have an h-square error decay. And that's pretty cool, because we could numerically verify that this actually works. Let's draw some conclusions. As you have seen, the topic of estimating errors is difficult, and it's not really satisfying in terms of the results, because you usually can only give qualitative results, talking about convergence and how fast error is decaying, and not quantitative statements that actually tell you the error is this and that big. In our case, the convergence prerequisites are the same as for unique solutions, so especially boundedness and coercivity for the bilinear form. This underlines even more why it's important to check these properties, because if you have them, you are completely golden, because you know that your problem has a unique solution and your FEM is also giving you the best approximation in the respective space, and you get convergence, so everything is perfect. And then this concept of convergence can be proven analytically, and it also shows in simulations. Of course, in most practical cases, you don't know the exact solution, but you still, if you know that it is converging, you can use this fact, because you can, for example, try to do some estimation of the limit towards which the error is converging, or towards the limit towards which the numerical solutions are converging, and then this can be interpreted as the exact solution. And it's also possible to construct so-called multi-grid methods. So these are methods that are acting on different grids. So you do FEM solutions on a coarse grid and on a more fine grid, and then you try to know more about the solution by looking at the differences between the two grid sizes. And as a last step for today, I want to give the final remarks for our course, because this is the last lecture, and I want to shortly summarize what we have done. So this course was called Finite Element Methods, Theory and Application or Implementation. And as you see here, those individual parts, theoretical and applied parts, they contain of different individual parts that we have tried to discuss all in this course. So in the theoretical parts, those last two lectures, existence and uniqueness of solutions, and convergence and approximation quality. And in terms of applications, the previous 10 or the first 10 lectures where we talked about grids and function spaces, numerical integration, assembly, which is kind of a part of it all, and discretization in terms of time. So those many individual parts that you have seen, that all together form our finite element methods, and they only work if you have all of them. So if you don't have a grid, there is no use in defining function spaces. If you cannot numerically integrate, you can't actually assemble the process. If you don't know that you have a unique solution, you probably get a super terrible result, and so on. So all these individual parts combine to forming our finite element method. So let's summarize for a second what we talked about grids. So it's crucial for the construction of any FEM to have some computational grid. Shape regularity, which I've drawn here on the right hand side again, is a very important thing. Shape regularity talked about the longest edge compared to the in-circle diameter. You wanted those triangles to not be super long stretched, but more equal in terms of shapes. Then for every type of grid, you wanted to find a reference configuration that is very simple. For our triangular grids, for example, we've chosen this simple reference triangle between 0 and 1. Then we also thought about the fact that finer grids give you a higher approximation quality, but also require more computational resources. Then we had different types of grid storage, those direct storages and the hierarchical storages. And then we have also seen that local refinements, as seen down here, for example, in this Shishkin type grid or in the locally refined grid near the phase field interface, they can be a very powerful tool to optimize between accuracy and performance. Also, there is a ton of stuff we haven't talked about in terms of grids, for example, for weirdly shaped domains, how you can get a grid there, then how to actually practically implement the recursive refinement algorithms and so on. So there is a ton to do about it. Then we talked about function spaces, and we have learned that there are different individual function spaces that all together form our FEM. We have the global function space formed of piecewise linear functions in the whole domain. And on each grid cell, we had a local space of functions which were actual polynomials on the grid cell. And then we had an additional local function space on the reference map, on the reference cell, which were again actual polynomials. And we have seen how to transform between them. Using the reference map, we could transform between the grid and the reference cells. And using the DOF map, we could identify the global basis functions with the local ones. Then we have also talked about degrees of freedom. We have seen that depending on the polynomial degree, you need to choose a different type of set of degrees of freedom locally on your reference triangle. This translates to local degrees of freedom on your actual domain, and then also some global ones. And we have always defined basis functions for the spaces, so basis for the global piecewise space and also basis for the local polynomial spaces, always using some Lagrangian condition, so wanting that a certain basis function is value 1 on a single degree of freedom and value 0 on all other degrees of freedom. That concept was preserved throughout the whole definition of those function spaces. Then we have also seen that numerical integration is a key part of FEM, because due to our weak formulation, those integrals occur naturally, and usually you don't know the primitive of the integrand, so you can't just analytically write down what the integral is. We have also talked about the approximation quality of quadrature rules, which is usually stated in terms of exact integrals of certain polynomials. This should be matching the chosen function space. So if you use local linear polynomials, then you should also use a quadrature rule that is exact for linear polynomials. And we have seen that Gaussian in 1D and Gauss-type quadrature rules in multiple dimensions provide the optimal exactness for a certain number of weights and points. So kind of the best you can get in terms of approximation quality for a certain number of points and weights. For example, you see here that this version for exactness 1 was just using the barycenter of the triangle as the quadrature point. And there's different other ways that you can, or other topics you can talk about when talking about integration. So of course you can define higher order formulas, and formulas that are matching different types of geometrical structures and so on. And also we talked about time discretization, because most problems that occur in nature and physics and in engineering, they are not stationary, so they involve time derivatives. We've seen that we need additional methods to discretize the time, which is in our case done independently from the space discretization with FEM. So we use the FEM and the grid and the local basis functions to deal with all of our spatial derivatives, and we do an additional time discretization with some standard scheme that we know from ordinary differential equations like Euler or some Runge-Kutta method to take care of the time derivatives. We've also seen that numerical stability is a big issue in the field of instationary PDEs, so you should always choose implicit methods. You see here on the right those two examples for the simple ordinary differential equation with the green exact solution, where you had this huge spiky behavior in Euler's explicit formula, which should not be the case. So you should always take care of stability there. And then when talking about time-dependent problems, there is a huge potential for optimization, because you can always think about if a certain coefficient function is actually depending on time or not. And if something is not depending on time, it can only be assembled a single time at the initialization of the whole procedure, and does not have to be assembled again every time. The next part we talked about in the last lecture was existence and uniqueness. Before talking about any numerical method like FEM, you should always know if there is a unique solution, because if it's not, then you are screwed, because you get completely weird and unhelpful results. Because the finite element method is built on weak solutions as a framework, it is necessary to also talk about solution theory in this setting. So you need to investigate solution theory and unique solvability in the setting of Sobolev spaces and variational problems. This usually involves linear and bilinear forms in Hilbert spaces, which opens the door to a huge amount of theory. And we have seen that if we prove certain properties for linear and bilinear forms, we can use like Smilgram's lemma to show existence and uniqueness for the solutions. And also we have seen that the question for unique solvability depends on the combination of many different parts, the domain, the PDE, and the boundary conditions. Here on the right hand side you see this scheme again, where I've computed the solutions to Poisson's equation and to some reaction diffusion problem. So different PDEs in this direction here, different boundary conditions, so Dirichlet boundary conditions here and Neumann boundary conditions here. And you've seen that 3 of those variants give you perfectly fine results, while the last one up here, Poisson's equation with Neumann boundary conditions, gives you just no information at all. So yeah, you see that it's always important to talk about existence and uniqueness before actually trying to apply a method, because otherwise you might end up with something like this, coming out of your simulation. So imagine how annoying it is if you would spend hours of simulation time on some high performance computer, and what comes out is something like this, and the only reason for this is that you haven't spent enough time to talk about unique solutions. That's super annoying and it should not happen. So always make sure that you have well-defined problem statement. And then the last part today was to talk about approximation and convergence. So we have seen in the beginning that the same numerical setup can create immensely different results, some of which are pretty good and some of which were plain and simple terrible. And it's usually not possible to find the an exact quantification of the error because the analytic solution is just not known. Instead, what's usually done is you talk about convergence, so how fast the error is decaying if you consider a finer grid resolution. And we have seen that this convergence rate depends on the chosen norm, but it's also in any case possible to numerically verify those theoretically predicted values by doing this type of convergence study, plotting it logarithmically alongside with the asymptotics, and then we could see all of this. This is kind of the end to the course, but of course there is more to be studied here at our university. So I want to name a few further courses that can be interesting and are in the same direction. Firstly, the course Pde Numerics, which was taught at the same time as our course, and the advanced course, so Pde NMW, that is the advanced concepts for Pde Numerics, that is taught in the summer. There you get a much deeper understanding of the theoretical groundwork for FEM. So how does the solution theory work, especially how does the convergence and all of this error quantification that we have just taken a very, very short glance at today, how does this work? Then the course Pde Analysis, so a very theoretical course talking about the real mathematics and a very abstract setting of embedding all of this FEM theory into the abstract concepts of Sobolev spaces, more general Sobolev spaces. That's pretty interesting because there they actually do all of the proofs that you need to show and to well understand how all of those spaces are working. And then some courses from our own institute. So the course Scientific Computing, which is taught every summer semester, is talking about advanced topics in modeling. For example, this Alan Kahn model, which I've shown you in the adaptive grid lecture, so this phase separation process, that has been a topic of this SC Comp course in the last years, but also other modeling topics. Then we have scientific programming, which is also taught in summer. This deals with efficient implementation. That is also something we have completely neglected in this course, talking about efficiency. So efficient implementation for advanced methods, for example, good linear solvers, specifically defined for FEM, or in general, the implementation of fast assembly processes and so on. So this is more from a technical point of view. Then we have the modeling seminar in summer and the modeling project in winter, which is called slightly differently for people from CMS programs, but it's essentially the same concept. So you're doing a seminar and a project about modeling and simulation. So using all those things that you've learned about FEM and PDEs on some applied project. And then we have different other optional courses that happen sometimes. So for example, MMRM, which is mathematical courses on real or advanced applied mathematics, some seminars also. So we had courses about numerics for singularly perturbed problems. As I have mentioned in the respective lecture, there is potential to talk about this for a whole semester. So there is different things to be done. And the last thing I want to show you is that we have student research positions available. We have master thesis and PhD thesis topics available, and something more. Just a quick teaser here. This is a part of my own research, talking about describing cellular structures, for example, in your skin, by partial differential equations, and analyzing the collective behavior of those cellular structures and the formation patterns. So yeah, if you are interested in pursuing some research position as a student worker, or try to do a master thesis or get a PhD position after finishing your master's, just contact me and we can talk about this. And this is all I have to say in this course about finite elements. So I'm very thankful for the huge audience I had, and I'm thankful for all of your patience with those with the topics. And I wish you all the best of luck for the rest of your studies, and also, of course, for the exams. And maybe, I will see and hear you again in some other course. Thank you very much.